Welcome to AI Frontiers, where we explore the latest advancements at the intersection of artificial intelligence and human curiosity. Today, we are diving deep into the dynamic world of computer vision, a field that has captivated researchers and practitioners alike with its potential to transform how machines perceive and interpret the visual world. Over the past few decades, computer vision has evolved from a niche area of study into one of the most vibrant domains within artificial intelligence. Its applications are vast, ranging from autonomous vehicles navigating complex urban environments to medical imaging systems aiding doctors in diagnosing diseases with unprecedented accuracy. This episode synthesizes recent breakthroughs in computer vision research, drawing on groundbreaking papers published on May 18, 2025. These studies highlight the current state of the field and point to exciting future directions. By examining dominant themes such as parameter-efficient fine-tuning, few-shot learning, and multi-modal integration, this narrative will take you through the intricacies of modern computer vision while maintaining a focus on accessibility and engagement for our scientifically curious audience. To fully appreciate the significance of these advancements, it is essential to understand the broader context of computer vision within artificial intelligence and machine learning. At its core, computer vision seeks to replicate and enhance human-like visual perception in machines. This involves teaching computers to recognize objects in images, interpret scenes in videos, reconstruct three-dimensional structures from two-dimensional pictures, and even generate new visual content. The importance of this field cannot be overstated as it underpins countless technologies that impact our daily lives. Consider autonomous vehicles, which rely on computer vision to detect pedestrians, read road signs, and navigate safely through traffic. In healthcare, computer vision powers advanced imaging systems that assist radiologists in identifying tumors or fractures with greater precision. Beyond these practical applications, computer vision continues to push the boundaries of what machines can achieve in interpreting the visual world, driving innovation across industries. A prominent theme in recent computer vision research revolves around visuospatial cognition and reasoning. Qi Feng and colleagues introduced ViCA2, a model designed to enhance spatial reasoning capabilities in tasks involving video-based spatial cognition. Their work achieved state-of-the-art results on the AIGIBench benchmark, demonstrating the effectiveness of a dual encoder architecture that combines semantic understanding with spatial analysis. This approach allows models to capture both high-level semantic information and detailed spatial relationships, making significant strides in fine-grained spatial understanding. Such advancements underscore the growing importance of specialized architectural designs in addressing complex visuospatial challenges. Another significant theme in recent research focuses on object tracking and state estimation. Jirong Jia and team developed DIMM, a framework that improves the accuracy of three-dimensional object tracking through decoupled multi-hierarchy filtering. This innovative method enhances motion description by expanding the model combination solution space from a hyperplane to a hypercube. Compared to existing state estimation methods, DIMM achieved accuracy improvements ranging from 31.61% to 99.23%. These results highlight the potential of advanced filtering techniques to revolutionize applications in autonomous navigation and surveillance systems. Multimodal integration has also gained traction as a critical area of research in computer vision. Maoyan Ye and colleagues created LogicOCR, a benchmark that evaluates large multimodal models' logical reasoning abilities on text-rich images. Additionally, the SSR framework bridges depth perception with textual rationales, transforming raw depth information into interpretable textual descriptions. Meanwhile, VideoRFT introduces reinforced fine-tuning approaches specifically designed for video reasoning capabilities in multimodal language models. These developments demonstrate how combining different types of sensory information can lead to more comprehensive scene understanding, reflecting the growing recognition that true visual intelligence requires synthesizing information from multiple sources. Among the key findings across these papers, compact models like ViCA2 have been shown to outperform larger counterparts, as demonstrated by Qi and colleagues. DIMM, developed by Zhirong Zha and team, achieves significant accuracy boosts in three-dimensional object tracking, with improvements ranging from 31.61% to 99.23%. Meanwhile, AIGIBench, introduced by Li and colleagues, highlights gaps in real-world AI-generated image detection, revealing performance drops in practical scenarios. These findings collectively underscore the diversity and complexity of challenges that researchers are addressing in their quest to advance computer vision technology. Several common methodologies emerged across these studies, each contributing unique strengths and facing distinct limitations. Dual encoder architectures gained prominence, particularly in visuospatial reasoning tasks, by combining semantic understanding with spatial structure analysis. Attention mechanisms and hierarchical processing were exemplified by Zhirong Zha and team's DIMM framework, which uses an attention-based twin-delayed deep deterministic policy gradient method with hierarchical rewards. Frequency space analysis, demonstrated by Ruoqi Wang and colleagues, manipulates amplitude spectrum and pixel content to enhance out-of-domain robustness. Meta-learning approaches, as seen in CJ Zhao and team's temporal-spectral-spatial unified strategy, leverage meta-information to standardize input representations across different data characteristics. Each of these methodologies contributes valuable tools to the computer vision researcher's toolkit, though their successful application typically demands careful consideration of both their strengths and limitations. One seminal paper comes from Qi and colleagues, whose work on ViCA2 represents a significant leap forward in visuospatial cognition. Their primary objective was to address the persistent challenge of fine-grained spatial understanding in multimodal language models. To overcome these limitations, the researchers designed a dual vision encoder architecture that integrates two specialized components: SIGLIP for semantic interpretation and HIRA for structural spatial analysis. This innovative architecture is further enhanced by a token ratio control mechanism that optimizes computational efficiency while maintaining high-performance standards. Evaluated on the challenging VSI-bench benchmark, ViCA2 achieved remarkable results, outperforming significantly larger models like Lava Next Video 72B and Gemini 1.5 Pro. The significance of this work lies in its demonstration that carefully designed compact models can achieve superior performance in specialized tasks. Another groundbreaking contribution came from Zhirong Zha and colleagues with their development of DIMM, a novel framework for three-dimensional object tracking. The primary objective of this research was to address two fundamental limitations in existing interacting multiple model approaches: constrained solution space and inaccurate combination weights due to measurement uncertainty. To solve these challenges, the researchers designed a 3D decoupled multi-hierarchy filter bank that expands the model combination solution space from a hyperplane to a hypercube. Additionally, they implemented a differentiable adaptive fusion network that generates more reliable combination weight matrices through an attention-based twin-delayed deep deterministic policy gradient method with hierarchical rewards. Compared to existing state estimation methods, DIMM achieved accuracy enhancements ranging from 31.61% to 99.23%, representing a significant advancement in three-dimensional object tracking technology. A third seminal paper comes from Li and colleagues, who addressed the pressing issue of artificial intelligence-generated image detection through their development of AIGIBench. While numerous detectors had been proposed with high reported accuracy, their effectiveness in real-world scenarios remained questionable. To bridge this gap, The researchers created a comprehensive benchmark designed to rigorously evaluate the robustness and generalization capabilities of state-of-the-art detectors. AIGIBench simulates real-world challenges through 4 core tasks: multi-source generalization, robustness to image degradation, sensitivity to data augmentation, and impact of test time pre-processing. Through extensive experiments involving 11 advanced detectors, the researchers revealed significant performance drops when these models were applied to real-world data. This comprehensive evaluation framework provides valuable insights into the current limitations of artificial intelligence-generated image detection technology. Looking ahead, several promising avenues emerge for future research in computer vision. One significant direction involves developing more efficient and less resource-intensive methods, as many current approaches require substantial computational power and large datasets for training. Future work could focus on creating lightweight models that maintain high performance while reducing resource demands, building on innovations like parameter-efficient fine-tuning and few-shot learning techniques. Another critical challenge is improving the robustness of models across different domains and conditions, such as adverse weather for depth estimation or noisy data for self-supervised learning. Addressing these challenges will likely involve advances in model architectures, training strategies, and data augmentation techniques. There is also a growing need for more comprehensive benchmarks and datasets that reflect real-world diversity and complexity, as highlighted by the introduction of AgroMind and HyperCap. As the field progresses, increased emphasis will be placed on explainability and interpretability of computer vision models, alongside efforts to make these technologies more accessible and deployable across various industries and applications. This episode was synthesized using AI tools including GPT, qwen-max, TTS with OpenAI, and Grok for visuals. While reviewed by human experts, it acknowledges potential oversights and provides references for all synthesized content. The synthesis process leverages cutting-edge technologies to ensure accuracy and accessibility, enabling us to bring you the latest breakthroughs in computer vision and artificial intelligence research. In this podcast, we bring you the latest breakthroughs in computer science and AI straight from the archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.